So let's take a look at motion, specifically dealing with velocity and acceleration. So in Calculus 1 and 2, you might have had a look at particle motion. And so the position function in terms of time t is written as s of t. And so if you derive position, you'll get the velocity in terms of t, which is going to be s prime. And then let's say you derive velocity, you'll get acceleration in terms of time t. That'll be equal to v prime of t, or also equal to the second derivative of the position. But now in Calculus 3 we're looking at vectors, and the good thing is it works the exact same way. So instead of s of t we have a vector function which also gives the position, and that's written as r of t. Now if you derive r of t, you'll obviously get the velocity vector, or the velocity vector function in terms of t. So that'll be equal to r prime of t. And then if you derive velocity, you'll get back to acceleration here. And so that's going to be v prime of t, and once again r double prime of t. And also remember that speed is going to be equal to the magnitude of the velocity, because speed is another word for the magnitude of the velocity. And so it works the same way for vectors as well. It is also going to be equal to the magnitude of v of t, or in other words the magnitude of r prime of t as well. And so another way you can write speed is also with the Greek letter upsilon. So for these next set of problems, let's go ahead and find the velocity, acceleration, and speed of the particle with the given position function. So for number 1, our position function is r of t equals e to the ti plus e to the negative tj. So let's go ahead and find first the velocity. So the velocity, remember, is going to be the derivative of the position function. So the velocity in this case, we're going to have to derive r of t. So we take the derivative, first we take the derivative of e to the t, and so the derivative of e to the t is still going to be e to the t. So you have e to the t times I, and then plus the derivative of e to the negative t, and so that's going to be negative e to the negative t times j. And so when we evaluate, we'll get e to the t I, and then this time minus e to the negative t j as the velocity function. So now let's go ahead and find the acceleration function. So remember, acceleration is going to be the second derivative of the position function and the first derivative of the velocity. So if we go ahead and take the derivative of the velocity here, derivative of e to the t is still e to the t. We get times I and then minus. Now the derivative of e to the negative t is going to be negative e to the negative t times j. So notice the negatives will cancel, so we'll get a positive. And so the acceleration vector is going to be e to the ti plus e to the negative tj. So now let's go ahead and find the speed. So remember, the speed is going to be equal to the magnitude of the velocity. Okay, so if we take the magnitude of this, remember the magnitude is going to be the square root of the x component squared, so e to the t squared, plus the y component squared, so we have negative e to the negative t. When we squared, that negative will go away, so we'll basically have e to the negative t, the entire thing squared, and then plus the z component, but realize there is no z component, so that's going to be 0. So when we evaluate, now e to the t squared can be rewritten as e to the 2t, because when you have power to a power you can multiply. So we get the square root of e to the 2t, and then you get plus e to the negative 2t. So that is going to be the final answer for the speed of the particle. So now for number 2 we have r of t equals sine of ti plus t times j plus cosine t times k. So let's go ahead and start with finding the velocity. So the velocity function here is going to be the derivative. So the derivative of sine of t is going to be cosine ti, plus the derivative of t, which is simply just 1, and then 1 times j will just give us j, and then plus the derivative of cosine, which is a negative sign, so we can write it as minus sine t k. So that is going to be the velocity function. So now moving on to the acceleration. Acceleration we're going to have to derive once more. So deriving the velocity function here, derivative of cosine t is negative sine t, so we get negative sine ti. Now the coefficient in front of the j is 1, and the derivative of 1 is 0, so we get 0 times j. And then the derivative of negative sine is going to be negative cosine, so minus cosine tk. The 0 and the j will cancel, and so we're left with negative sine ti minus cosine tk as the acceleration function. Now once again, in order to find the speed, it is going to be the magnitude of the velocity. So the square root, we're going to take the velocity, we're going to look at the velocity function here, take the x component squared, so cosine squared of t, plus the y component squared. Now the y component is simply just 1. 1 squared is 1, and then plus the z component squared. So that is going to be sine squared of t. Once again, cosine squared plus sine squared equals 1, and 1 plus 1 equals 2. So we're going to get the square root of 2 as the speed. So once again, speed can either be written as the Greek letter upsilon, or it could also be written as this way, the magnitude of simply the velocity. So for this next problem, let's go ahead and find the velocity and position vectors of a particle that has a given acceleration and the given initial velocity and initial position. So for number 1, we have a of t, the acceleration function, equals k. Now the initial velocity here, v of 0, equals I minus j, and the initial position, r of 0, equals 0. So now notice it asks us to find the velocity and position vectors, but it's giving us the acceleration. So if we derive velocity to get the acceleration, then we must integrate acceleration to get to velocity. So let's go ahead and integrate the acceleration vector with respect to time. So we do that, we must integrate k. And so now the coefficient in front of the vector, unit vector k, is 1, and so the antiderivative, or the integral of 1, is simply just t. So we get tk. Now there's another way you can think about this. If you write k in component form, k is obviously going to be equal to 0, 0, 1, because the x and y components are 0, but the z component is 1. So that's going to be equal to k. And so if you take the integral of k, you must take the integral of each individual component. Now the integral of 0 is obviously going to be 0 still. Integral of 0 is 0, and the integral of 1 is just going to be t. And so if you rewrite this one in unit vector form, this is simply just going to be tk. Remember, this is an indefinite integral, so we must add the plus c. So if I were to rewrite the velocity function here, v of t is going to equal to what we got here, so t times k plus c. So now we need to know what that plus c is, and so notice it tells us, or gives us the information, that v of 0 equals I minus j. So if we plug in 0 for t here, we get 0k plus c. And so v of 0 is equal to I minus j, so we can go ahead and replace v of 0 with I minus j. So I minus j equals 0 times k is simply 0, and we get c. So c is equal to I minus j. Now if we go ahead and rewrite the velocity equation, now v of t is going to be equal to tk plus c, which is equal to I minus j. So we get plus I minus j. So if I rearrange all the unit vectors, v of t is going to equal, let's put I first, since that's the x component, then minus j, and then plus tk. So now let's go ahead and find the position vector. So the position is obviously going to be the integral of velocity. So let's go ahead and integrate this vector function here. So when I do that, the position function r of t is going to be equal to the integral of the x component, I. So now the coefficient in front of I is simply just 1, and the integral of 1 is t. So we get ti. Now the integral of the y component, the coefficient in front of j, is going to be negative 1. And the integral of negative 1 is negative t. So we get minus tj. And then the integral of t is t squared over 2. So we get plus t squared over 2k. And then since this is indefinite, we have to add that plus c. So now we know that r of 0 equals 0. So if I plug in 0 for t here, r of 0 equals 0 times I, which is 0, 0 times j, which is 0, and then 0 squared over 2 is still 0, so that's going to be 0, and then we'll get c. And r of 0 is equal to 0, so we can replace 0 with r of 0, which tells us that c is 0. So if c is 0, that means our final equation for the position vector, r of t, is going to be just as it is, and we make c 0. So we can cross that out. So we get ti minus tj plus t squared over 2k. So now for the next set of problems, we're going to talk about tangential component of acceleration and the normal component of acceleration. So let's say we have a position graph of a particle, so let's just label it S of t. And so now let's say starting from this point here, we have an acceleration vector. Let's go ahead and call that A. And so in order to understand the motion of a particle, sometimes we need to understand the components of its acceleration. And there are two components, so this one right here, since it's tangent to the curve, this one is going to be called the tangential component of acceleration, so A sub t. And the one that is normal or perpendicular is obviously just going to be called the normal component of acceleration. And so given a vector function or a position function r of t, the formula for the tangential acceleration component is going to be r prime of t, the dot product of r prime of t and r double prime of t, over the magnitude of r prime of t. The dot product of r prime of t and r double prime of t over the magnitude of r prime of t. And so the normal component of acceleration formula is going to be equal to the magnitude of the cross product of r prime of t and r double prime of t over the magnitude of r prime of t. So let's go ahead and find the tangential normal components and normal components of the acceleration vector, given that r of t equals 3t minus t cubed I plus 3t squared j. So the formula for the tangential acceleration component A sub t is once again going to be equal to the dot product of r prime and r double prime over the magnitude of r prime. So let's go ahead and find r prime and r double prime first. So r prime of t is going to be equal to the derivative of the x component, which is 3t minus t cubed. So the derivative of that will be 3 minus 3t squared I. Remember, the entire thing is being multiplied by the unit vector I, since the entire thing is part of the x component, and then plus the derivative of the y component, such as 6tj. And now r double prime of t is going to be once again equal to the derivative of the x component of r prime, so that derivative is going to be negative 6t to the first I, and then plus the derivative of 6t, which is 6j. So now let's go ahead and take the dot product of r prime and r double prime. So the dot product, once again, we're going to multiply the similar components. So we're going to take negative 16 and multiply by 3 minus 3t squared. So we get negative 6t times 3 minus 3t squared. And then we add when the y components are being multiplied together. So then 6t times 6 is 36t. So now when I go ahead and distribute over the negative 6t to 3 minus 3t squared, we'll get negative 18t plus a positive 18t cubed. Then we have plus 36t. So negative 18t plus 36t would be positive 18t. So we get 18t cubed plus 18t. So now let's go ahead and find the magnitude of r prime. So the magnitude of r prime once again is going to be the square root of its x component squared. So we get 3 minus 3t squared, the entire thing squared, and then plus the y component squared. So 6t squared would be 36t squared. Now we'll go ahead and FOIL this. So we're going to end up getting the square root of 9 minus 18t squared, and then plus 9t to the fourth, and then plus 36t squared. So if I go ahead and simplify, we'll get negative 18t squared plus 36t squared. And I'm also going to rearrange the terms so that the highest degree, 9t to the fourth, is going to be on the left. So we'll get square root of 9t to the fourth. Then once again, negative 18t squared plus 36t squared gave us a positive 18t squared. And then we have plus 9. Now what I'm going to do here is go ahead and factor out 9. So the square root of 9 times t to the fourth plus 2t squared plus 1. So since these are being multiplied here, the square root of 9 is 3, so I can bring that outside of the radical. And notice that this is a perfect square trinomial, so we can factor that into, so I'll put 3 times the square root. Now we can factor this into t squared plus 1 and the entire thing squared. So notice when we take the square root of something squared, it's going to cancel. So we're left with 3 times t squared plus 1. Or in other words, 3t squared plus 3 as the magnitude of r prime. So now that we have the dot product of r prime and r double prime and the magnitude of r prime, let's go ahead and find the a sub t, or the tangential component of acceleration. So once again, that is going to be equal to the dot product, which we got 18t cubed plus 18t divided by the magnitude of r prime, which we got 3t squared plus 3. So to go ahead and simplify, I can actually factor out a 6t from the numerator. So we'll get 6t times, now we get 3t squared plus 3 over 3t squared plus 3. Notice they will cancel, and so we're left with 6t as the tangential component of acceleration. So now let's go ahead and find the normal component of acceleration. So the normal component, once again, this time it's going to be the magnitude of the cross product of r prime and r double prime of t over the same thing on the denominator here, the magnitude of r prime of t. So we've already found the magnitude of r prime, so let's go ahead and keep that answer. So now all we have to do to find the normal component of acceleration, we must take the cross product and find the magnitude of the cross product of r prime and r double prime. So let's go ahead and take the cross product. So once again, when we take the cross product, we must set up a matrix. So we have I, j, and k on the top, and then we have our components. So since r prime is being multiplied first, let's write it down its components first. So r prime's components, its I component is going to be 3 minus 3t squared. For j, it's going to be 6t, and it has 0 for k. And then for r double prime, it's going to be negative 6t for I, 6 for j, and 0 for k once again. So now let's go ahead and put it in determinant notation. So when we do that, we take the top left most term, so I, we cross out its row and column, and we write what's left inside a smaller matrix. So what's left is 6t, 0, and 6, 0. The second term is going to be a negative. So we have negative j, cross out its row and column. So what we have left is 3 minus 3t squared, 0, and negative 6t and 0. The third term is going to be a positive, so plus k. Let's go ahead and cross out its row and column. So we have 3 minus 3t squared, 6t, and then negative 6t and 6. So now let's go ahead and evaluate by cross multiplication. So we have I times, now 6t times 0 is 0, minus 0 times 6, also 0, minus j times, that times 0 will give us 0, and we'll also get another 0 when we multiply negative 16 and 0. And then plus k times, well, 6 times 3 minus 3t squared will give us 18 minus 18t squared. And then minus negative 6t times 6t is negative 36t squared. When we subtract a negative, it's going to be a positive 36t squared. So the zeros will cancel out I and j. And so we're left with k times, well, negative 18t squared plus 36t squared will give a positive 18t squared. 18t squared, and then plus 18. So if I rewrite this, I can also rewrite this as 18t squared plus 18 times k. So that is going to be equal to the cross product of r prime and r double prime. So we have found the cross product, but now we need to find the magnitude of the cross product. So once again, in order to find the magnitude, we'll take the square root of the x component squared. So realize there is no x component because there is no I vector. So that's going to be 0, plus the y component, which is also 0 because there's no j, and then plus the k or the z component, which is associated with the k unit vector. So we're going to take 18t squared plus 18 squared. So these are just going to cancel, and the square root of something squared will cancel. So we're left with 18t squared plus 18 as the magnitude of the cross product of r prime and r double prime. So now the normal component of acceleration is going to be equal to what we just found, 18t squared plus 18 over the magnitude of r prime, which we found earlier to be 3t squared plus 3. 3t squared plus 3. Let's go ahead and factor out a 6 from the numerator. So we get 6 times 3t squared plus 3 over 3t squared plus 3. They will cancel, and so we're left with 6 as the normal component of acceleration.